Hello, good morning everyone. My name is IVGS, currently pursuing my BTech in Electronics and Communication Engineering in GM University. My details are mentioned below. Today I am presenting an project design and simulation using LTspice with respect to the topic that is MOSFET characteristics where it is variation with ID, VGS and VDS. So let's begin.
Welcome to the Technical Competency project. My topic is on MOSFET characteristics. MOSFET is nothing but a voltage control device. Here we considered N-channel MOSFET and we are discussing the working procedure. So this is the structure of a MOSFET where S, G, D junctions will be present. So when gate voltage is higher than the threshold voltage, the MOSFET will be in the cutoff region. So you can see here the cutoff region is the point of the graph will lies in the x-axis along the x-axis where we can measure the VDS. So now the first condition we will discuss about the VDS. The VDS, the VGS will be constant. So when here you can see that the no electrons or holes are contributing each other. So in the source and in the drain, the electrons will be constantly in that phase. So in this, the depletion region will occur. So here the current from drain to the source will not occur. So the MOSFET in this condition will be in off condition. So therefore we get the cutoff voltage region as a constant linear at VGS axis. VGS axis. So now to flow the current, we will consider the VGS by keeping the VDS as a constant. So now from the drain to the source for the current flow, we will connect a VGS. After the connecting VGS, the electrons and holes will flow between them. So substrate as a PT, holes are majority charge carriers and electrons are minority charge carriers. As you see here, the holes will be accumulated in the top side of the MOSFET and the neutrons will be accumulated and the negative charges will be accumulated between the S and D junction. So here you can observe that the graph is linear still. So when it is allowed the electrons to passes through them, here there is a development of a region that is called as a N-type semiconductor region. So after this, the electrons will be flow from between the S and D, between the source and drain. So the electrons flow here in the circular path. So there is a so there is an increase in the VGS where we can see here in VDS there is an increase in a current with respect to the voltage. So as we see the increasing, if we increase the gate and the continuous increase of voltage with respect to the threshold voltage, the cutoff region will also increases. With respect to finally we will get the pinch of voltage and saturation region. So here you can see the pinch of voltage and the saturation region with respect to the VDS and IDS. And here you can see the ID and VGS characteristics graph with respect to the gate voltage and drain voltage. This is the final graph we will get. So now we will implement this in the LTspice. So firstly, we will see that the circuit diagram of this MOSFET. In this circuit diagram, we have considered the VGS and the VDS where the current flow will occur. So through the resistors load and the two resistors here VG is connected and VDD is connected. So in this circuit we will measure the current with respect to the voltages given with respect to VDS and VGS. So let's enter into the simulation part in the LTspice. So let's begin the LTspice simulations. I am already did the MOSFET design in this LTspice. So this is the VGS and the VDS. We consider the VGS as a 10, VDS as a 30 with respect to the NMOS. Here we considered a N channel MOSFET. So it is a NMOS. We considered as a R2 and R1 resistance. R1 is about 10 and auto resistance is 220. So here, now we will start the simulation. So first in configuration analysis, go to the DC sweep. We can vary the first source, second source, third source. So I can vary three sources at a time. Now I will vary the first source. That is, we will consider VGS. We will consider VGS as variation and VDS as a constant. So now first the which is varying, VGS is varying, right? Take here the VGS. Now type of speed. We can we need the graph like linear, right? So press on the linear. The starting value of the linear and the stopping value of the linear. So starting value I can expect from 0, right? 0. Then stopping value I will keep about 10. So the increment of the each duration I will keep it as a 1 volt. So this is the details of the first source. This is details of the first source. Keeping the VDS as a constant, right? So now we will see the graph. So we will measure the current at the NMOS where at the drain current. We need the current right at the drain. ID current we need. So see, this is the graph we are getting with respect to the ID, with respect to ID and VGS, keeping VDS as a constant. So you can see here the 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. So this is the individual increment. How much I gave? 1 volt. So it is a increment of a 1 volt with respect to each other. So now press on I. You can see the match point of the 5 volt. Now right click on it, and you can press on the view. You can mark the data points. So the data points are marked with respect to the increment. Here one need to play increment, right? So it with respect to the one increment, the current will be measured with respect to the voltage. This is the characteristics of a transfer characteristics. Now we will see the characteristics of drain current. Drain characteristics we will see now. So now we will keep VGS as a constant and we will vary VDS. So this will become a drain characteristics. So as of now, press on this, press on this. So now we will vary with the first source and only the second source. First source we will consider as VDS. It will be a linear 0, and we will stop time we will consider as a 30, and the increment we will consider as zero point 0.1. How much you can want, that much you can do that. I considered here as a zero point 0.1, and in the second source I will consider as a VGS. VGS, and the graph type of sweep will be linear, and the start value is 0, and stop value will be a 10, and increment I took as a 2, 2 volts. Press OK. Now you can see here the VDS is set to 30 volts, and with the zero point 0.1 voltage increment, VGS is set to 0 and 10 with the increment of 2. So now measure this, run the simulation. See, now you can see the graph of ID and VDS, where VGS is a constant as we consider. So now this side is a ohmic region, and this side is a saturation region. The line which is zero point 0.0, that is green line, that line indicates a cutoff region, right? Cutoff region. So when we consider VGS as a 0, 0, the VDS is measured to 0 to 30. VGS is measured at 0, VDS is measured at 30. So we will get the 0 to 2 volt difference. That is red line. Okay, from 0 to 4. 0 to 4 means VGS is set to 4 voltage, VDS is set to 0 to 30 with a step zero point 0.1 voltage. We will see the next line. And as we increment the VGS with respect to the current as 0, 0, 2, 4, 6, 8, as we increases that we will get a different types of graph with respect to red, blue, pink, light black. Like that we will get the graph. So here this is ohmic region, this is saturation region, the green line is cutoff region. In the ohmic region, the MOSFET will be considered as a current source where voltage will be neglected. And in the cutoff region, the line in which is in the cutoff region, the MOSFET will be here, the current will be zero and the voltage will be variation. So here in the saturation region, it is not widely used, it is considered as a resistance will increases here. So this is about the simulation of the LTspice. Thank you for giving this project to us. Thank you, one and all.